Welcome to lecture 52, segment 1, where we're going to talk more about ignition and extinction. And actually, we're going to solve an example to clarify all of this. Example 8.9c. Okay, you all remember example 8.9a, where we had CSTR with a cooling coil. Okay, and in that case, we had a single steady state. That's example 8.9a. However, in this example, we're going to have multiple steady states. Okay, so let's revisit example 8.9a and change the following parameter, where basically the reaction there was A plus B gives you C, which basically was propylene oxide, as you can see here, propylene oxide plus water in the presence of a catalyst. As you can see here, you get a product which is propylene glycol. Okay, so let's change a few things for example 8.9. So we would have a new example, 8.9c. Okay, the delta H reaction here, we're taking it as a constant value. So that's a constant value. And T naught, I believe T naught there was maybe 75 degrees C. Now here we have 52.5 degree Fahrenheit, which is around 512 degree Rankine. And we are also changing the ambient temperature. We're changing the ambient temperature. There was around 85 degree Fahrenheit. Here we're changing it to 50 degree Fahrenheit. And finally, we're reducing the volumetric flow rate of water. Okay, so basically the water flow rate is dropped to half. Right. What does that do to the other variables? Think with me. If we reduce the volumetric flow rate of water, what would happen? Yeah, that would affect the volumetric flow rate going to the reactor. Exactly. And that's the new calculated value. And it will also affect the tau, the space-time, right? Because you know tau is basically V over epsilon naught. So epsilon naught is current to it's reduced. Okay, so tau will increase. Okay, what else? Yeah, of course, you got it right. When you change epsilon naught to, that's the volumetric flow rate of the water, obviously you're changing the molar flow rate of water as well, the entering molar flow rate of water, which you are dividing into half. Okay, and that will also affect the theta b, as you can see. Okay, these are the changes that we introduced to example 8.9a, and now we have a new example that is 8.9c. Again, CSTR with a cooling coil and multiple steady states. Okay, what's required? Well, concerning the heat generated and heat removed, let's derive expressions for GT and RT. Let's do that. Okay, how do we proceed? Let's first find expression for GT and then go to RT. Okay, but let's start from the energy balance. Let's start with the energy balance. Okay, so we have here FA naught times summation of theta I CPI times T minus T naught plus FA naught times X times delta H reaction. That equals Q dot minus shaft work. Assume negligible shaft work, although we have shaft work because it's a CSTR, but let's assume it's negligible. Okay, what else? Well, we want to find GT, so let's take this term to the other side, and now we have FA naught I'm gonna, instead of writing summation of theta I CPI, I'm just gonna write CP naught. Okay, if you agree, then multiply by T minus T naught. I'll bring the Q to the other side, so that's minus Q dot equals, take this guy to the other side, so we have here minus FA naught X times delta H reaction. We can divide by FA naught, and we'll have CP naught times T minus T naught minus Q dot. How do you quantify Q dot? You quantify it as U times A times T that is outside, TA minus T inside, and this is divided by FA naught equals X times minus delta H reaction. Okay, so let's see, where is GT and where is RT? Now we have here GT and this is RT. Okay, and then I promised, let me define where CP naught equals summation of theta I CPI. And what's that? Well, we look at the feed. What do you have in the feed? You have A, you have B in the feed. Do you have anything else? Well, yes, you have methanol, right? So that's M. Okay, so let's do that. So that will be CPA plus theta B times CPB, and we don't forget the methanol, it's an inert. It goes into the summation of theta I CPI. So that's theta M times CPM. Okay, that's great. So we have expression for GT and RT. We can write them individually if you like. Okay, so let's write them individually. So that's GT equals X, and X from where? We're going to get X from the material balance, times minus delta H reaction. What about RT? RT in our case was, oops, what happened? Okay, we had CP naught times T minus T naught minus U times A divided by FA naught times TA minus T. Okay, excellent, Shabab. Very good. So now we have developed expressions for GT and RT. Great. Next, show a sample calculation for each at temperature of 519.3. Okay, so we need to show how to calculate the GT and how to calculate RT. Let's do that. So for GT simply, in order to calculate GT, we need, as you know, that we'll need GT equals X material balance times minus delta H reaction. So first thing we need is X material balance. Where are you going to get it from? Well, obviously you're going to get it from the material balance. And for the material balance, of course, we write the design equation. That was V times FA naught times X divided by minus RA. And of course, we write the rate law, which was minus RA equals K times CA. It was first order with respect to A, okay, because B was provided in excess. Next comes the stoichiometry. We had CA equals FA divided by epsilon, and of course FA equals FA naught 1 minus X, and epsilon equals epsilon naught. Why is that? It's a liquid phase reaction, and therefore you have CA naught times 1 minus X. Okay, and then what's next? Well, we could really combine, right? Okay, let's combine then. So we have V equals FA naught times X, and then we have minus RA equals K times CA, and for that we write CA naught 1 minus X. Okay, so we can go further, and we have here V equals, the FA naught could be written as CA naught times epsilon naught times X divided by K CA naught times 1 minus X. Okay, can we simplify? Yes, we can. Let's simplify. This guy cancels out. Okay, we can divide by epsilon naught. Okay, and of course we know that this guy is tau, right? This guy is tau. Okay, so let's rewrite it. I'm looking for a place to write all of this. Let's write it here for now. So we have tau equals X divided by K 1 minus X. Okay. Yep. Okay, and then if we solve for X, then we get the X material balance. That would be, I'll leave the details of calculation for you to do. So that's X material balance equals tau times K divided by 1 plus tau times K. Do you memorize this equation? Do we memorize this equation? No, we don't. This is a result of the manipulation, right? Okay, so we'll do that. Okay, so let's go to another page to get some space. So here we are again. Let me write the X material balance. X material balance equals tau K divided by 1 plus tau K, where K equals Arrhenius constant times minus E over R T. Okay, that's really great. Okay, so can we calculate now XMB and therefore calculate the GT, which was XMB times minus delta H reaction? Can we do this? Yes, we can, because once we plug the temperature here, okay, we can calculate K. Tamam, we already calculated tau earlier. Of course, I'm not going to the step-by-step calculation. Okay, so you have to do the step-by-step calculation yourself. Okay, that's tau. We can calculate XMB, and now that we have XMB, tamam, we already, this is given, we can calculate GT. So now we have a value for GT, and actually the temperature was specified, I believe it was at around 519.23, maybe something like that. Okay, so we calculate it and get the value. Okay, this is a quick sample calculation for GT. What about a sample calculation for RT? Well, we wrote the equation for RT. As you remember, let me use another pen here. Okay, let me use black. So we calculated RT to be simply Cp naught times T minus T naught minus U times A divided by Fa naught times Ta minus T. Okay, that's really great. That's really great. Okay, so sample calculation, yes, we can do. So we already showed that equation of Cp naught, so you can calculate Cp naught. T naught is already given. Tamam. U times A values, this is given, this is given, this is given, and T is also given. So all what you need is to plug in the value of T here and value of T here. Okay, and which was 519.23, I believe. Okay, and then you get the value for RT at 519.3, and here we go. Okay, that was really easy. What else? Okay, now we need to plot GT and RT versus T. Well, we have the equation for GT and we have the equation for RT, so it's very simple to plot these versus T. How do we do this? Well, for me, of course, I used Excel, the same Excel what we developed in the earlier lectures. Okay, I'm using it here with a slight modifications. Okay, so this is the T which I'm varying, and after I vary T, I calculate K. And of course, the value of delta H reaction is given, so it's very easy to calculate XMB. Okay, it's very easy to calculate XMB from the expression of XMB that we just developed. Okay, and from XMB you can calculate, of course, value of GT. Okay, and then as we just showed, it's also easy to calculate RT. Okay, and then now we can drag everything and we can plot. This is the plot of GT, tamam, and for RT, of course, it will be a straight line because it's function of T and T to the power 1, and then you have a slope and intercept. And this is the RT, as you can see, it's a straight line. Okay, that was really simple, huh? Excellent. Anything else needed? Okay, let's see what else is needed. Okay, so it's very simple to read the steady state temperature. Let's read it together. Okay, this is the lower steady state temperature. You go down, vertically down, and that's around 520. Okay, this is the middle steady state. That is slightly bigger than, larger than 560. So maybe that's 562.5 maybe, or something like that. Okay, and the upper steady state has a temperature of somewhere around 515 maybe, 615, sorry, Franken. Okay, so now we know how to read the steady state temperatures. Of course, which one you recommend to operate in? Well, this temperature is good in terms of it will give you high conversion. However, it's too high, right? Remember, we don't want to exceed 585 degree Rankine, 125 Fahrenheit, because otherwise boiling will, the mixture will lose lots of the propylene oxide. Okay, you don't want to do this. Would you operate in this temperature? Of course not, because this is unstable steady state. You can tell that when you compare GT to RT with a slight disturbance. You can see to the right, GT will be more than RT, and therefore the temperature will shoot up. Okay, so the steady state will shoot to the other steady state, and if with a little bit disturbance to the left, you can see that GT is less than RT, so RT is more than GT, so it will keep cooling to the lower steady state. Okay, so you want to avoid this. You want to avoid this to avoid evaporation of propylene oxide. So your only bet is to operate at the lower steady state. Okay. Okay, good, excellent. What else? So now we calculate the conversions at the lower and upper steady state and comment on their stability. I'm gonna just do one of them, you do the other one at home. Okay.